In this section, we're going to learn about sequences and difference equations. A sequence is a list of numbers written in a definite order. As a notation, we usually look at the terms of a sequence and use A with a subscript. So A1 or A sub 1 is called the first term, A sub 2 is the second term, and in general, the A sub n is the nth term. Sometimes we want to start the sequence with n being 0. So we say the 0th term or the initial term is A sub 0, and then we label the rest of the terms the same, A1, A2, A3, all the way to an. Notice, for every positive integer n, there is a corresponding numbers A sub n. So the sequence can be written as a function. The domain of that function would be the set of positive integers, and then f of n would give us the terms in the sequence. But usually when we have a sequence, we use the notation A sub n. So let's look at an example. Here we want to write the first 5 terms of the sequence A sub n equals -1 to the power n minus 1 over quantity n plus 4. And that's for n being greater than or equal to 1. So our first term is going to be A sub 1. And to find A sub 1, we're going to just replace all the n's with 1. And we'll have -1 to the 1 minus 1 power over 1 plus 4. 1 minus 1 is 0. -1 to the 0 will be 1. So in the numerator, we have 1. On the bottom, 1 plus 4 is 5. So we get 1 over 5. And then we'll continue. We're asked to do this for the first 5 terms. So for A sub 2, we'll replace n with 2. We have -1 to the 2 minus 1 over 2 plus 4. 2 minus 1 is 1. In this case, -1 to the first power would be negative. So we get a -1 over 6, or -1/6. So for A sub 3, we have -1 to the power 3 minus 1. 3 minus 1 is 2. -1 squared would be +1 over 3 plus 4, which is 7. So +1/7. For the fourth term, we have -1 to the power 4 minus 1. -1 cubed is -1 over 4 plus 4, which is 8. So -1 over 8. And finally, for our fifth term, we have -1 to the power of 5 minus 1. -1 to the fourth power is +1 over 5 plus 4, which is 9. So +1/9. This gives us our sequence to look like this. 1/5, -1/6, 1/7, -1/8, 1/9. And now I can see the next term's going to be -1 over 10 because my terms alternate in positive to negative to positive to negative. And since I have 1/9 in the fifth term, the sixth term is going to be -1 over 10. And the following one would be a +1 over 11. We call a sequence that looks like this to be a harmonic sequence. In this case, it's an alternating harmonic sequence because our signs alternate. And we can take a quick look at what these would look like if I plotted them. And we'll see these numbers plotted would be alternating up and down around the axis. And they're getting closer and closer to becoming 0. And again, we'll look at what we call the convergence of these sequences in future sections. Next, we're going to look at the same process in a way going backwards. We'll start with a sequence of numbers and try to come up with the formula that generates them. So here is our sequence: -4 over 3, 5 over 9, -6 over 27, 7 over 81, and so on. And we want to find a general term, A sub n. So a formula that will let me generate any term I want in the future of this. So we've got to do a little bit of detective work here. we'll look at the different parts of this and see if we can generate a formula. So our first term in this case is a negative 1/3. So when we plug in 1 into our formula, in the numerator I should get a 4, in the denominator I should get a 3, and the sign needs to be negative. When I plug in 2 into the same formula, I should get a positive fraction where the numerator is 5, the denominator is 9. When I plug in 3, I should get a negative fraction. The numerator should be 6, the denominator 27. For the fourth term, we need, when we plug in 4, we should have a positive 7 in the numerator and 81 in the denominator. So let's stop and take a look. And the first thing I need to ensure is that my signs do what they're supposed to do. So we'll notice in here, when I plug in an odd number, so 1 or 3, my fractions are negative. When I plug in an even number, my fractions are positive. So that part could be accomplished by starting our sequence formula with negative 1 to the nth power. Right? So negative 1 to an odd power would give me a negative answer. Negative 1 to an even power would give me a positive answer. Next, if I look at the numerator, we start with a 4. And then our terms keep growing by 1. Right? So if I want the first numerator to be a 4 when I plug in 1, I need to have 1 plus 3. And then the second term, 5, would be 2 plus 3. 3 plus 3 would give me 6. 4 plus 3 would give me 7. So it looks like if I use n plus 3 in the numerator, I'll be able to get the numbers that I have currently. So we have a negative 1 to the nth to ensure the signs alternate, and then n plus 3 to make sure we get 4, 5, 6, and 7. Then when we look in the denominator, we'll notice that the numbers are all powers of 3. So I have 3, then 3 squared is 9, 3 cubed is 27. So at 3 to the first, 3 to the second, 3 to the third, 3 to the fourth for the fourth term. So if I write my formula as a negative 1 to the n times n plus 3 over 3 to the nth power, I'm going to get the sequence that we're looking at. Now, sometimes we don't have a defining formula like we've had in the previous two examples for our sequences. In those cases, we may be able to write a formula for the nth term of a sequence that depends on some of the terms that came before it. That sort of a formula we refer to as a recursive formula. So here's an example. We want to write the first 5 terms of the sequence given by a sub 1 equals 1. And a sub n plus 1 is given to be 3 times a sub n plus 5. So that means for us to move from one term to the next, I need to take the term that I have multiplied by 3 and add 5. And that will let me move on to the term n plus 1 from the term a sub n. Right, so notice the first term was given to me in this case because our formula is recursive, and if I don't have the first term, I cannot proceed to the one after. Sometimes I need to be given more than the first term, depending on how the sequence is defined. We'll look at an example shortly. So here are my first terms. The first one is already given. So I need the next 4 terms. The second term would be 3 times a sub 1 plus 5. A sub 1 was given to be 1, so 3 times 1 plus 5 is 8. The third term would be 3 times the second term plus 5. 3 times 8 plus 5 is 29. The fourth term would be 3 times the third term plus 5, 3 times 29 plus 5 is 92. And finally, the fifth term in this case would be 3 times a sub 4 plus 5. 3 times 92 plus 5 is 2AD. One of the better known sequences that appears in nature is called the Fibonacci sequence, named after the 13th century Italian mathematician Fibonacci, who used it to solve a problem concerning the breeding of rabbits. The sequence occurs in numerous applications in plant biology. So a typical Fibonacci sequence requires me to have the first two terms, and then the subsequent terms are found by adding the previous two terms together. So this is how it would be defined. In this case, the first term and the second term are given to be 1, both. And then the third term would be the result of the sum of the two previous terms. Now, again, notice I needed to be given two terms because I need two terms to add together to find the term that comes after it. So here, our third term would be the result of adding the first two terms, so 1 plus 1 is 2. The fourth term would be the result of adding the second and the third term together, 2 plus 1 is 3. Fifth term would be adding, again, the terms that came before it, 3 and 2 give me 5. And then one after that would be 5 plus 3, which is 8. And 8 plus 5 is 13. So in general, this is what the Fibonacci sequence is going to look like. 1, 1, 2, 3, 5, 8, 13, 21, 34. The term after that would require me to add 21 and 34 together, and that would give me 55.